Okay. So
you need to accept it from your file. You need to accept that.
you're telling me so many things that I don't know. Accept,
Yeah.
reject, ignore. Where?
You have to go to Zoom.
Right?
Yeah, right. Now, 1 second. Where is Zoom? Yeah, look, you have to got it. Now it's accepted.
Okay, got
Now,
it.
yeah. Now you can
Now it's recording. Great. So homework number 2, you said it's long.
A little bit. Yeah. I felt like that. I didn't read it.
Okay, anybody has the solution manual for the textbook? Good question, right? You're smart, right? I know. Please give it to me. Okay. You have the solution manual, okay? So you have the solution. Very good.
I think so.
So it means that everybody will get 100 out of 100. No, right?
I think the instructor, they can ask it directly from the publisher.
No, you are here. I don't need to ask the publisher, right? This is a shortcut. Anyway, if you have it, just upload it in the group. Okay, very simple. Okay, here it's to learn. It's not about. It's okay. I know the solution. You can even ask for solution. You can buy solution manual, right? If you are rich enough, you can buy solution manual. Do you think that will give you a plus in the course? No. Even if you have the solution manual, still you have to do the problem. Still you have to understand the problem, right? So, my advice: can you send me the solution manual in the group? Okay, and I'm not going to change the problem anyway. But definitely in the exam, it will be a different problem. And that's the real test. Okay?
You want to know who directly flow the solution manual.
Huh?
If you have the solution manual, you can pick out the person who copied.
Why do you have to chase people? Copy anything you like. Copy anything you like, but the problem, if it comes in the exam, do it. I'm not here to be a judge, right?
I have the solution manual for the first edition.
No, there is a solution manual for this one, I'm
This
sure.
one I don't have it. I have
You don't have it,
the
but many have it. Many, the others have it. Yeah, you will see it. Anyway, don't send it to the group. Send it to me and I upload it. That's better, right? Privacy, right? Okay. Send it to me. Huh? SI, same as the book. SI. So that's it. You have the homework and you have the solution for the homework. Now, are you ready to submit the homework?
Yeah.
Okay. Very good.
Next Sunday.
Next Sunday. Right. I don't have to work with this machine, right? See, my default is taking me here. Okay. Now, let's have the. How do you move the? I'm using the arrows, but the arrow is not working. Escape. Space. Space will work.
Yeah.
Did we do this problem?
Yes.
Yes. Okay. This is what? If somebody asks, what is this? Everybody with me now. You have to be all on track. Okay. This is what? This is transformation. No. This is the stiffness matrix of 3D truss element in 3 dimension, right?
Yeah.
With respect to the global system. Those who are coming here, they didn't come last time. You have a member. Truss.
The local.
This is local.
Yeah, global.
This is global because there is CX, CY, CZ. So basically, if you have a truss member, and this is node I, and this is node J, and this is X, Y, Z. The direction or the location of this truss what comes the global axis? The global axis should be x should be along the member, right? You remember this?
Yeah.
This is your x prime. This is your y prime, and this one here is z prime. So the prime system is called local. The x, y, z, the unprime system is called global. Okay, so I don't need z bar, I don't need y bar. The only thing I have to define is the location of x bar with x, x bar with y, and x bar with z. So x bar with x, we call it alpha. X bar with y, we call it beta. And x bar with z is gamma. And then we define cx, cy, cz. Anybody will tell me what's the cx? Cosine what?
Alpha.
Cosine alpha, cy, cosine,
Beta.
and then cz
Cosine
equal
gamma.
cosine gamma. That's it. And once you know the direction of alpha, beta, gamma, then you can find what? You can find the stiffness. Okay. In fact, we solve a problem here. We solved this problem, if you remember. You have to read at home, really, because every time you come to me here, as if we are saying it for the first time, you just tell me, we know it, go ahead. And this is what? What is this? To convert the displacement to stresses, right? So this is like C prime rho with displacement, right?
Yeah.
Is this scalar or scalar?
Yeah.
This is always, we call it transpose. Always, any vector, D, if you put D like this, it means what? It means column. If you put D transpose, it means what? Row. Anytime you see transpose, it means row. Anything that you didn't see, we'll talk about it now. Okay. Yeah, we'll talk about it in deriving something else. Okay. What is this? Did we do this problem? This is symmetric one. What is the idea about this? You divide it to two. There are two things you have to do. You have to divide what? You have to divide the load. Instead of 2P, you have to use P. And then what else?
Stiffness for number 4 and 5.
The stiffness for 4 and 5, you have to divide by 2. That's it. You have to divide by 2 the stiffness. Because you are slicing it, okay? So you are using half of the stiffness to the right. Look, we use the left part. We put P, but 4 and 5 is half of the stiffness, okay? So you can see that, wow, we got theta. What is this theta? This is alpha. You see, we only need to define alpha. Alpha with X, alpha with Y, and alpha with Z, right?
Yeah.
Which is CX. This is 2D. Okay, which means alpha, which means X prime with X and X prime with Y. So it is C and S. Okay, 2D. I think we got 3D, right?
Yeah.
Let's talk about this. What happened here? If you have a truss like this, you can see here.
We already done this.
Well, no, we didn't do it exactly. I just say it, but I don't explain it. So I'll explain it now. Okay. Now, what we have here? One, two, three nodes. And how many members? 3 members, 2 supports. Okay. The problem here is that we always need to define our boundary condition with respect to the global. But the problem sometimes we cannot define it with global. Like support number 1, you will say U1 is 0 and V1 is 0, right?
Yeah.
But you cannot say U3 is 0 and V3 is 0. You cannot define it with respect to X and Y. So you have to define it what? With respect to the local. It means you have to talk about U prime or U3 prime and what? V3 prime. Okay, which one is 0? V3 prime is not, V3 prime is 0. But U3 prime is, okay. How many unknowns in this problem? Remember, the unknowns are the displacement. How many unknowns? Are you sure 3? Yes, 3. Because in 2, there is no support. So you'll have what? U2 and you have V2 And you have what? U3 prime. It means you are mixing sometimes global and sometimes local. If it is inclined, you have to define it with local. Okay? If it's not inclined, then you can define it with global. So you will see now we are going to have mixed mode. Okay? So how do we do that? The problem here, you can see here that this is the local displacement. You are making them global displacements through transformation. You already know that. Okay? This is what? Global displacement. If you multiply by the transformation matrix, which is 2 by 2, you get what? Local. Okay. How do you go to local? This is the local. This is the transformation. We call it T1. And this is D. Now, how do you find D? If you want to find global, what do you do in this equation? 3.9.4. You have to multiply both sides by T1 transpose. So this one will be T1 transpose, right? This one will be T1 transpose. And if you multiply here by T1 transpose, it will be identity, right? So you'll get D. So you'll get this. Do you agree? Do you agree that D will be equal T1 transpose times D prime? Yes. So where do you need transformation? You didn't need transformation for node 1. You didn't need transformation for node 2. Only you need transformation for node 3.
Yeah.
This is why. Identity, transformation. Now, can you tell me this square submatrix, what is the size of that?
The small?
The small one, the one inside, like I, 0. 2 by 2. Because the transformation, already you have it 2 by 2 cosine sine, right? It's 2 by 2 because you have only 2 displacement. This is 2 dimension. We talk about 2 dimension, okay? So this one here, the T1 will be, what is the size of T1? 6 by 6. 2 by 2, 2 by 2, 2 by 2. If you don't understand, you have to ask me, okay? Who didn't answer? Who didn't understand this? You have 3 supports. Node 1, node 2, node 3. For node 1, global. So you put I. For node 2, you put I. Also identity. I means identity. 1, 1, 0, 0. Right? And 0 matrix means 0, 0, 0, 0. Okay. So you will use this as your transformation. Look here. This is your transformation. What is this? Local. What is this? Global. Okay, let's talk about global U1 V1 with local U1 prime V1. What do you think? It will be the same, right? Because this is 0 and this is 0. You will have these zeros. Okay, what about node 2? Global, you multiply it by identity equal to local. So it means what? Same. Look at node 3 where you have inclined support. Do you think global is the same as local? No. Global U3 V3 equal transformation times local. So you can see here that you have to have that. You have to have transformation like this. But this is only intermediate step. This is not the whole step, okay? So we want to get something like this. I hope you understand this page. This page is crucial. Okay. The first one, do you understand the first one? The local equal transformation times the global. We have it before. Okay, now how do you go from 3.98 to the other one? What did we do?
399.
No, how do you go from 3.9.8 to 3.9.9?
This is a normal equation.
They have nothing to do, right? They are independent. One is transformation and the other one is the force equal stiffness times the displacement, right? They are not related. Okay. Now go to this equation and multiply the second equation by T1 here, okay? And T1 here. K is K. And instead of D, I put what? T1 transpose D prime. Do you agree? Okay. Now, you are the boss in mathematics, mashallah. Right? Can you multiply three matrices together
Yes.
using Mathematica, and you give me a big matrix? You can do it, right? Have you noticed something here? Notice here. What happened? For 1 and 2, you put it global. For 3, you put it local. Look at the forces. The forces at node 1 and node 2 global. But the forces at node 3 is what? Local. So it's mixed mode. Okay. Once you have inclined, then you cannot specify things in global. You will get the forces in local and specify the displacement in local. But you have to use T1 K, T1 transpose. Okay. You want a problem? Okay, let's see this problem. But this we are going to use equation 3.9.14. So what do you want to do first? You find K1, K2, K3. Get the big K, global stiffness, K. Right? Okay. So what do you want to do in this problem? Look at this problem. So there's node 1, node 2, node 3. Okay, it says for the plane, the display, determine the displacement and reaction. A is given, element 1 and 2, they have the area. Okay. So what do you think? This is 2D. So what is the size of K for each element? 2 by 2. In global, it will be 2 displacement, U and V, right? So it is 4 by 4. Yes, look. Element number 1, it's connecting node 1 with node 2. So U1, V1, U2, V2. Okay, for element number 2. Global. We didn't talk about the support here. Okay, even for element 3, U1, V1, U3, V3, everything with respect to the global. So the total stiffness will be with respect to the what? Global. Okay, can you assemble those?
Yeah.
Yes, it's here. So this is U1, V1, U2, V2, U3, V3. What is U3 prime and V3 prime? Not here. You have to apply it in the equation. The only thing now you have is what? Capital K. So you have only this. You have to know what is T1 multiplied by T1 transpose. Okay. So we finish now capital K. T1, node 1, what? 2 by 2 identity. Node 2, identity. Node 3, this is the transformation. CS, C, C, S minus S, right? Okay, take this one, multiply it by transpose and do everything. You see, T1 K, T1 transpose. If you do all of this, you get this. But now, once you multiply them together, then you have U1, V1, U2, V2, but you don't have U3, V3. What you have? U3 prime, V3 prime. You have different steps. Easy. Now, can you tell me what would be the forces? It would be what? F1, F1X, F1Y, F2X, F2Y with respect to the global. And for node 3 will be F1X, F2X, F3X, F2X, F2Y, F3X prime, F3Y prime. Okay. And do you have the K? Yes, we have the K in front of you. This is K. Can you tell me what is in here? U1, V1, U2, V2, U3 prime, V3 prime. Now, you need to tell me about 6 that you know, because now 12 we have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have only 6. Okay. We go back to that. Okay. Yeah. Do you know what is U1 and V1? Support 1, hinge. We know them. Support 1. Okay, you want to see the figure? Okay, the figure. Okay, the figure. Okay, U1, V1. How much U1? Equals 0. Equals 0. Unknown, right? Okay, unknown. Unknown.
Unknown.
Huh?
V2 is
For the support 2.
Zero.
Which one is 0?
V2 is 0.
Okay, this is 0. Okay, what about this one?
Unknown.
Which one is unknown?
U3
prime?
Both are. Both.
No.
U3.
You get it. Roller. So which one is 0? Which one is 0? V3 prime, right? It cannot move perpendicular. So V3 is 0. So now very good. You found what? 4. You need to have more, 2 more. Okay, let's go to the forces. F1x, do you know it? Reaction. F2x, reaction. Let's go to note 2. Do you know F2x?
Yes.
So how much is that?
1000.
I don't know. What's the unit? Okay, maybe you need to multiply times 10 to the power 3.
Up.
Not this one?
2x. This is unknown.
Okay, this one.
Yeah.
What is 1,000?
1,000 kilonewton.
Okay, times 3 Newton. Okay, what else?
Unknown.
Unknown. What about here?
That is the 3x prime. No. 0. 0.
Which one is 0?
That is 3x prime.
Is there any force in the x prime?
No.
There's no force in the x prime.
No, this is 0.
Wow. 1, 2, 3, 4, 5, 6. Very good. You will extract what? How many unknowns here? How many unknowns?
2.
Oh, no, only 2 unknowns.
2 unknown.
2 unknowns. Because you have to solve for the displacement. You don't talk about reaction. Reaction later will come. So the unknowns here is U2 and U3 prime. How do you do it? Can you tell me? Partitioning. So you will come here. We'll make a line here like this in column 3, right?
Yeah.
Yep.
And this is column 3. And then what is this? 5?
Yeah. 5. Row 5.
And this is 5. And how do you do it?
V2 take the.
In fact, you can generate the equation. You can write what? 1,000 times 10 to the power 3 equals. So the third row by the column. So this one will be 0, right? 0, some value here, times U2, and then what?
Plus 0,
0, and then some value here,
No.
Times this one, U3 prime, right?
Yeah. The above the value is going to be the other one.
The body.
No. This one here. You have to talk about this row.
Yeah.
This row you multiply it by this column, right?
Okay.
So this is 0. We don't have it. This is 0. Then this x times U2.
Yeah.
Then what is it? 0. Then this one. That tick is here. Very good. You are really so focused. Times U3 prime. You agree?
Yeah.
Okay. Can you generate the second equation? Okay. Let's just see the 2 equation with the 2 unknown U2 and U and what? V3 prime. Let's just see. I want to see U2 and V. It is here, right? Did you see it? What did you see? No, U2 and U3 prime. U2 and U3 prime, right? U2 and U3 prime. Okay, can you solve for U2 and U3 prime?
Yeah.
Can you solve for the forces?
Yeah.
Yes, just substitute. Interesting, right? This inclined support. Okay. The idea here that you have a mix between global and local. Okay. Local if it is inclined, global if it is fixed. Okay. This end up, I think, the presentation for this one. Okay. Let's see the other one. Where is the other one? Stop share. Okay. Stop share, and then
Open the next presentation.
share screen. It's here. Is it this one?
No, not this one. You have to open the presentation. This one. You can share the screen and then you can open whatever.
In WhatsApp.
You just share the screen first.
Share screen. Share screen. Okay, share screen.
So at the top, you just click share.
I will click share.
Now you can open whatever. there it's recording.
Okay.
Go ahead.
I think now you can do the homework. This is for the next homework. This potential energy is for the next homework. But this one here, how many minutes? We have half an hour.
Yeah.
That is the heart of the finite element method. You have to focus with me in this derivation, okay? It's very, very important. We are doing it for the rod. Then we will do the same thing. We'll repeat it for the beam. Then we'll repeat it for the plate. Then if you understand this, you'll be on solid ground, okay? Very good. So, space, right? You told me to do space, right?
Yeah.
To go to the presentation. Are you sure this is, okay, the objective here to derive the bar equation using the theorem of minimum potential energy, right? We didn't derive it for the truss. We derived it for spring. Okay, so we'll do that. And then we'll compare the solution of finite element with the exact. Okay, have you seen this equation 3.10.1 in spring? Yes, you did the homework already. You know that you need to calculate two quantities. The first quantity is called what? Strain energy. The second quantity is called potential energy. And the other one, total potential energy. Okay. So for spring, by the way, you asked me there is a problem of this F equal to K delta square, right? You asked me about this. This one here, the different answer because the units for K is wrong. Because you should have force. You should have force. So this one is force per unit per meter square. So that 112 by meter square, you get force. You should figure this out, right? So K is different. Not K is always Newton per meter. If you say F equal to K delta square, then K will be Newton per meter square, and delta will be meter square. Then the answer of F will be in Newton. Okay, coming back to this anyway. So this is a rod here, and we are talking about 1D, and there is a force P. What happened to this? It will create stress, sigma X, uniform, and it will create strain. So now we want to get U and potential energy for this rod. So how do we do it? We do it through using small element and we integrate over the volume. In other words, we find the strain energy for a small volume. This is what they do in math. And then you integrate over the whole volume. That will give you the total. You see, look at this element. We took an element here, and that element has the dimension delta X, delta Z, delta Y. So the force here, the stress here is sigma X. So how much the force on the element? The force on the element, how much? It will be sigma X times the area of the element. So it will be sigma X, delta Y, delta Z. Okay? Do you agree? This is delta Y, delta Z. So how much the work done? It will be the force times the displacement. So the force is sigma X, delta Y, delta Z times the displacement. How much the displacement? Displacement will be delta X times d strain X. You remember strain X? Strain is equal change in length divided by the original length. Here, your original length is dx. Your strain is delta epsilon X. This one here is your delta, okay? How much the displacement? So how much the displacement here? How much the displacement? It's delta X. So you have to multiply delta X, which is like the original length, delta X, times strain on that element, which we call it delta strain. Okay, this will be clear in the next slide. Here we go. If you multiply sigma X times delta Y, delta Z, that will be the force. If you multiply the force by the displacement, and the displacement will be delta X times d strain X. This will give you the internal strain energy. But this is per what? Per unit volume. So if you want to go about U, what do? You multiply it by dV. Do you agree here that this delta Y, delta Z, delta X is called delta V. It's the volume of the element.
Yeah.
Now, this is du. Why we put du? Because this is the strain energy for the element. du strain energy for the element. So how do you get the strain energy for the whole bar? This is dV. You integrate over the volume. If you get the triple integration, and you will get this one here is the strain energy. Okay. To keep this in one hand, and imagine you have this is sigma x, and you have it's linear. We talk about linear. This is sigma x, and this is epsilon x. The area under this curve is what we call U star. Strain energy density, or strain energy per unit volume. What is the area? What's the area under this curve? Half sigma x epsilon x. Do you agree?
Yeah.
What is this? This is not the strain energy. This is the strain energy per unit volume. So if you want to get the strain energy, what do? You take this, you multiply it by dV and integrate. That will be U. This one here, we call it U star. So what's the difference between U star and U? U star is like density, strain energy per unit volume. Okay? If you multiply it by dV and you integrate, you will get what? U, which is the total strain energy. Okay? We understand this point. 2 points. Half sigma times epsilon is what? U star, strain energy density. If you want to get the total strain energy in the bar, you have to integrate over the whole volume of the bar. Okay. Now we need to do what? Omega. Is this called omega? Okay, omega. Okay. Omega is the external work. So the external work done with a minus sign will give you the potential energy. What kind of forces in the bar? There are 3 kinds of forces. There is body force, the weight, body force, forces which are applied on the surface, and concentrated load. Very simple. Distributed load, distributed force, which is like traction, body force, and concentrated force. These are the 3 forces, right? So there are 3 terms here. The first one is the body force. You integrate over the volume. Look here. You are multiplying what? Displacement times the body force. And this body force is what? Body force per unit volume. This is why you multiply the body force per unit volume times dV and you integrate. Okay, what about T? What is it? Traction, which means force per unit area. You have to integrate over the surface, the area. Okay, what about here F? It's concentrated force. You just multiply force times displacement. So one time you multiply directly the force by the displacement, which is concentrated force, which you can see at the node. Node 1, node 2, there is F1x and there's F2x. These are concentrated force. We finished that. Okay, what about here? This is distributed force, which is on the surface of the element. Look at S1, dx, it's external, right? And you have to integrate over S, over the surface. Now the third one is what? Did you see X4? Did you see that? Yeah, it's per unit volume. So you multiply by that. So we take these 2 equations, we put them together. Wow, it's here. So what is this? Do you understand this?
Yeah.
What is this? Okay, it's here. Okay, what is if you have a road here? This road has an area, right? And it has what? dx. So dV will be equal the area times dx. Put the area dx here, so you have to integrate over the length. You see from where to x? So A times dx is what? dV. A is constant rod. Put it outside the integration, so you have to integrate over the length. This term here is what? U. This is the external work done. This is the work done on at the 2 nodes. This is for surface, and this is for what? Body force. So all of the force is here, and this one here. But anyway, we want to get to something like this. F equal to K times D. We want to reach to this. How do we do it? This is pi. This is the total potential. Remember, what do we do for the spring in order to get the stiffness matrix using minimum potential? You did homework. What did you do? Yeah, you have to integrate. You have to differentiate. You have to differentiate, right? Differentiate with respect to what? Nodal displacement with D1 and D2. Because you see, this one here is D2 and that one is D1. So, look here. This is D, you have to differentiate with D1x, get one equation, and differentiate with D2x, get another equation. And from there, you will get the stiffness. Okay. Okay, this is now a very good question. This is sigma x, this is epsilon. Is this a scalar?
Yes.
This is scalar.
Yes.
Scalar. What about this? Is it scalar?
Yes.
Yes, all of it.
All of scalar. No. What about here? This one is displacement function. Do you think this is scalar?
Yes. We multiply this one of them.
Oh, this is a vector. And this is a vector.
No,
This is a vector. And this is a vector. Look, the hat means vector. This vector.
not product,
Huh?
not product.
It's dot product, which means what? Dot product means what?
Scalar.
Scalar.
It means scalar. Scalar means what? That this is U transpose. And this is a row column. Because it's a scalar. That's why I explained to you about D transpose. So the first U is this is transpose. And the other one is this is why scalar. So scalar. This is what? Row. This is column. This is row and this is column. Okay, what is U? U in a vector form. We know it. U equals summation of Ui in I. Or if you want U, it's called what? N1, U1, right? Plus N2, U2. It's here. Look at it. U is a vector. This vector is called shape function, which is like row times the nodal displacement, which is column. See? N is a row. D is a column. So if you take N is a row and D is column. So what's the strain? What's the strain definition? By definition, what's the strain? Derivative of U. Yeah, strain is equal partial or du dx. Okay, so what does it mean? But U here, we said d dx of U. U, what is U? U is ni ui. Ui is nodal displacement. They don't change with respect to x. The only thing is changed with respect to x is n. It means what? It means dni dx ui. It means what? It means dn1 dx dn2 dx times u1 u2. So you are taking the derivative of the shape function. You are taking the derivative of the shape function because the strain here, look, strain is du dx. But you don't take the derivative of the nodal displacement. They are not function of x. They are specified at a certain location. So what you need to take the derivative of what? Shape function. And this one here is dn1 dx, and this one dn2 dx. Is this true? Okay, the first n1 is what? 1 minus x over r. Can you take the derivative with respect to x? 1 minus x over r. What's the derivative? The derivative of n1. n1 is 1 minus x over r. What is the derivative with respect to x? Minus 1 over r. Okay, what is n2? n2 is x over r. What's the derivative? 1 over r. So this is the derivative of n1, derivative of n2, and this is row, this is column, and you get this is this one, the derivative of the shape function, we call it B matrix. And you will see B matrix from now till the final. Don't forget. So if I tell you what is B, you tell me the derivative of the shape function. That's it. Okay? The B matrix is the derivative of the shape function. Yes. Yeah, because it's about displacement function. We are assuming that the displacement is linear. That's why you get the same thing. So it is linear in spring and it is linear in the road. Okay? So this is now the strain. Okay, very good. We have the strain. What else we need to go? Remember the pi. Remember the pi. All of what you are doing, you are finding this. What about the stresses? Because you have to put everything in terms of nodal displacement. How you are going to take the derivative of pi with d1x? Where is d1x here? We don't see it explicitly. That's why we put the strain in terms of the displacement, but we have to put also stress in terms of displacement. How? Modulus. Constitutive relationship between stress and strain, right? So sigma equal to E times epsilon. And this is only 1D. If it is in 3D, maybe you'll have sigma x, sigma y, tau xy. You'll have a matrix. And you'll have here what? Strain x, strain y, gamma xy. This one is called D matrix. So the relationship between stress and strain is called what? D. But for only special case that this D matrix become a scalar and it becomes E for the sake of uniaxial. Okay? So this is why we want to derive things in general. Look at it here. In general, you see sigma equal to D times epsilon, but only in this case because it's uniaxial, D equal to D. So what do you have? Strain, stress equal to what? D times epsilon. What is epsilon? B times D. Shape function, derivative of the shape function times D. Can you take this strain? Can you take this stress and you multiply it by BD and you tell me what would be strain energy?
What?
It's here. Okay. Look. You. Just you. What is you? You said it's half integral area sigma x epsilon x dx. Okay. A2. Okay, integral. We said sigma is what? Sigma from here. D is what? D times B times D. This is all stress. What about the strain? B and D dx. Is this a scalar or not?
Scalar.
Are you sure scalar? No, I don't see scalar here. What is the scalar?
At the end of it, scalar.
No, it will not be. It will not be scalar because D is what? 2 by 1. B is what? B, derivative of the shape function.
1 by 1.
It's either 1 by 2 or 2 by 1. You want it to do what? 1 by 2. Okay, 1 by 2. What about here?
2 by 1.
2 by 1. What about here?
1 by 2.
1 by 2. What about here?
2 by 2.
2.1? 2 by 1?
2 by 1.
This is not 1 by 1.
2 by 1 by 1.
The only thing you have to realize that you have to put the stress as a transpose vector and strain as a column. This is the only way to have a scalar. You have to put stress as a row, and you have to put strain as a column, so that when you multiply the row by the column, you get what? Scalar. So it means what? You have to put sigma transpose times epsilon. Because every time you see transpose, it means row. So you have to put the stress transpose. So you have to transpose this. Don't take the stress and you multiply by the strain. You have to multiply what? Sigma transpose times strain. What would be sigma transpose? Can you tell me from here? Sigma transpose will be D transpose. You have to change it. B transpose, then D transpose, then times strain. What is the strain? B, D. All of this is equal to a stress times strain. Okay, look at it here. Wow, it's here, yes. You see now? You see the stress transpose, D transpose, right? D transpose, B transpose, D transpose. All of this is what? All of this sigma. What is the strain? B times D. Very good. We finished now U. And this is scalar. If it is scalar, D transpose, it means what? Is it row or column? Row. What about B transpose? You multiply row by row. You multiply row by row. Row by column. Okay. Anyway, this is scalar. Okay. What about this? D transpose. Look. Load column. Look at the surface. You see D transpose. Every time the first one you put a transpose, it means row. The thing that follow it is column. Okay. Now, do you think everything has D now? Because we want to integrate with respect to D. Do you think everything has D?
Yeah.
This has D, D. This has D. This has D. This has D. Okay, very good. Now, I have to tie my shoes, right? Otherwise, I'll fall down. Okay, very good. Now, what is next you will do? Expand it, expand it, expand this, and take the derivative with respect to D1x, D1y. Okay? Okay. So what he did, he took, look, this is T transpose. This one, by the way, dt transpose is not function of the surface. So you can put it outside the integration. This one, dt transpose is not function of volume. So you can put it outside the integration. And then you can lump the three terms. In other words, these three terms, 1, 2, 3, you can lump them in one. And these are the force. Look, where is it? Where is it? Where is it? I wrote it here. I said at the end, I want to see F equal to K times D. I want to, this one here. So this D transpose, I can put it outside. In fact, I can, since it is minus, 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 I can put it in the left-hand side. Do you agree?
Yeah.
And that is the force. But this is before taking the derivative. And the right-hand side. And then I can take the derivative. Okay? Very good. So, look. Pi equal. This is the strain energy, and this is the omega. Okay. Now, how do you take the derivative of this? Do you see the three terms here? This is due to concentrated force. This is the force which is surface, and this is the volume. Okay. Now, take pi with d1x and pi with d2x. Now you come to dt, bt, dt, bd. What did he do? He substituted this. So d transpose, the first term is what? D transpose in pi. You have to tell me. D transpose the first term, and then multiply by B transpose. D. I want to have this in closed form solution explicitly. Okay? So explicitly it is here. Look at it. D1x, D2x. It's a row. B. Derivative of the shape function transpose. It's minus 1 over L, 1 over L. And then what about D? D is only E. E, 1 by 1. What about the shape function? Minus 1 over L, 1 over L. What about D? It is D1x, D2x. Do you think if you multiply all of them, they will give you scalar?
Yeah.
Yes, it gives you a scalar here. All of this, if you multiply it by the volume, which is area times L, that will give you. What about the other term? The other term, which is F. How did we get this? Can you tell me? It's only 2. See, explicitly D transpose. If it will give you only D1x, F1x, D2x, it would be, right? Because D transpose is D1x, D2x. It's a row. The other one is F1x, F2x. That's it. Row by column. Okay. Can you combine this with that? Because you have D1x, D2x everywhere. Wow. And then you take the derivative. When you take the derivative with respect to d1x, you get this equation. When you take the derivative with d2, you get this equation. So this is one equation and this is one equation. What do you want to do with this? Okay, phi with respect to d1x. It gives you one equation. Did you see that? Okay, anybody will tell me? Phi with respect to d1, dx1, and then phi with dx2. Okay, what's the first equation? Equal to 0. If it's equal to 0, I can put f1x to the left-hand side, right? f1x, this is left-hand side. What is remaining in the right-hand side? Can I put a L over E, and there is L square. So L with L square, you have it's A over 2L, right? Okay. Then times what? I can cancel the 2, right? Because there are 2 and 2. Why you have to have the 2? Cancel the 2. Okay, cancel the 2. Then what's inside? D1x minus D2x. Okay, what about the second equation? Second equation is same thing. L and 2 will cancel, so you'll have again EA over L. What? Which one here?
D2x minus D1x.
What?
D2x.
D2x minus
D1x.
equal to F2x. Okay, can you put it in a matrix form? Okay, matrix form to get the stiffness. Okay, I can put what? EA over L, and I can put it like this, equal F1x, F2x. Okay, from equation number 1, what should I put here?
D1.
Are you sure?
D1x, yeah.
This is D1x?
D1x minus.
D1x minus D2x.
It's 1 and 1. With minus.
Okay, multiply by D1x, D2x equal F1x, F2x. What's inside now?
One
Yeah.
minus one.
Right,
Minus
now
one.
you see. 1 minus 1 minus 1. That's it. We got the stiffness, right? EA over L, 1 minus 1 minus 1. Using the minimum potential energy. Okay. والله interesting, صح?
So much.
Okay. Okay. This is now the stiffness K, and it is coming with this pi with respect to D. Now you already know how to get the derivative with respect to D in explicit form. Can you integrate with differentiate with vector? If you differentiate with vector, you just remove the D. Look here. Look at the pi with D. I want to see the pi with D, not X. Did you see it here? Do you see the pi here? D transpose and D transpose. When you take the derivative of pi with D, you just remove the D transpose. In the first term, what is phi with respect to D? It will be A L over 2, then times what? B transpose, D transpose, B times D. Okay, what's about the second term? What is the derivative of the second term? Only F. That's it. Anytime you see any pi with D transpose in the beginning, then if you take the derivative, you just remove the D. Okay? Now, I guess you are fed up, right? Not really. Okay, just use this example. We have to give example before we leave, right? Okay, this is a very good example. Now, tell me how to find, I always go here. Okay, what about here? If this is node 1, this is node 2, and there is a load, this is traction, because you have 3 kinds of forces. It's either body force, nodal forces, or traction. When you have traction force, traction. Okay, what do you do with the traction? You have to integrate. You have to convert all the forces to the nodes. If it is concentrated, thank you very much. If it is uniform load, you have to throw some of it to this node and some of it to this node. If it is body force, You have to throw one to this node and one to this node. Now I'm giving you triangular node. Can you tell me how much of this node will go to node 1? And that's called F1x. And how much of this node will go to node 2, F2x? If you answer this question, we'll finish for today. Very simple. What do you think? First, by common sense and your intuition. What do you think?
Find the centroid of the loading.
Find the centroid of the loading?
Yeah.
Okay. Can you do this in your mind? Find the centroid of the loading and tell me how much the load.
Will be
Of course, the load is the force is the load is force per length. So first you have to calculate the resultant. What would be the resultant of the total load? It will be half the area, right? The area.
Yeah.
Half of L times
the maximum.
CL, because the height here is CL. At x equal to 0, 0. At x equal to L, it is CL. So what's the area of the triangle? So we are going to do it now, and then we'll do it by finite element. And you will see, we'll give the same answer, okay? Let's see. So how much the total load? You said half the total load. P, the total load, half CL squared, right? Okay. How much of half CL squared will go to node 1 and half of CL squared will go to node 2? I think 1/3 and 2/3.
Yeah, 1/3.
1/3 and 2/3. Okay. 1/3 of this. It means what? It means how much?
1/3 of this.
1/3 of this means it will be 1/6 CL squared. And here will be what?
2/3. So it will be 2/6.
1/3, right? CL squared over 3. Okay. This is, what about if I give you parabola? You have to use integration. This is easy now. The integration is the area. Now we have to use finite element. What about if I give you sine law? Sine. You have to use this. Do you remember this equation? That the load equal n transpose times T times ds. Right? We have this before. Rho, column, scalar, right? See? N transpose T ds. What is N transpose? N transpose mean, is it the derivative of the shape function? No. It is the shape function, but it should be column. So you see the column 1 minus x over L and x over L. And C is constant, so it is Cx. And then you put dx. So can you multiply this row, this column by this? Just multiply 1 minus x over L times Cx. You get this. Do you agree? Yes. And this one is that. Okay. Now, can we integrate it? What is the first term? What is the first term on the top? The first term before integration. Before integration, it will be what? It will be Cx minus Cx squared over L. Do you agree? So can you integrate it? Cx will become Cx squared over L. And the other term, which is Cx squared over L, will become what? Cx cubed over 3. So you get that after integration. And after integration, what is the second term down? XL times Cx. You get what? Cx squared over L. Integrated. It will be 6 cubed over L. And put the limit. Oh, this is it. Node 1. Okay, yes. Node 2. Yes. From the formula, from the form. So anytime you have any load. Now you can do it any load. Not only linear. What do? You put N transpose times a function, whatever function. You multiply them together and you integrate. Okay? Huh?
Wow, we put two signs of deduction. Signs of deduction. What are they? This one.
Why are there 2 signs of integration?
No, because it's an area, but because it is 1D, it's just because it's surface. Normally, when we integrate over the lake, we have one integral. When you integrate over the surface, you have 2 integrals. When you integrate over volume, you put 3. Okay. So this is bothering you, right? The 2 integral, right?
Yeah.
So we are changing the 2 integral instead of ds, we put the dx. So we change that 2 integral to an integral, right? Very simple. Okay, very good. Confusion is gone. Very good. Okay, now we have 1 minute, right? Only 1 minute left. Finish on time, right?
Right.
Wow,
Exactly.
good job. Great.
Right.
Okay, who's not here? Who's not here? Okay, now everybody decided upon the group, right?
Yeah.
Have you decided which two rooms? Okay,
We already recorded our names last class.
I don't know, there's a new guy here, right?
No, someone chose me.
Someone chose you. You didn't choose him, right?
Yeah.
Someone
I-
chose you. Who chose you? He's with you. Okay. Thank you very much. That's it for today.